Next, we reintroduce the concept of work. From classical mechanics, we know that if there is a displacement on the application of force, then we say work has been done. In mathematical notation, we say dW is equal to F dot ds, where F is the force vector, both are, and ds is the displacement vector, and the work is the dot product of force and displacement. We exemplify this definition of work with respect to compression and expansion of a gas cylinder. Let us have a piston inside which some gas are there. Before going to the derivation of expression of work for a piston, first we should say something on the sign convention of work we use in thermodynamics. Earlier, the sign convention was that the work done by the system was positive and work done on the system was negative. But recently the sign convention has changed, and we follow, this is actually the UPAC convention, and we follow that convention only. Now the convention is that work done on the system is positive and work done by the system is negative. Now let us discuss on the expression of work done for expansion and compression of a piston. First, let us define a coordinate system with unit vector attached to it as shown in the figure. We say on the that as shown above on the figure. Now dW, first let us discuss about expansion. Now we say work done on the system is positive. So whenever we in thermodynamics we consider about work, we will consider that some external force is working on the system. So the direction of force is shown in the figure, it is in the negative z direction. Now in case of expansion, the direction of displacement is on the positive z direction. So when we consider the work of expansion or work of compression, always the direction of force is toward downward. It means according to our unit vector system defined, it is towards minus k direction. And in case of expansion, the direction of displacement is towards positive k direction. So dW expansion will be equal to f dot dz. So now f can be a function of z. Okay, let us take f can be it is a function of z. So I can write fz dot dz. Now fz, I can divide fz by an area and also multiply by area. So the equation become pz dot dv, where dv is the differential increment, volume increment, and the direction of dv is I define here in the direction of dz. So direction of dv and direction of dz are same. Now p can be, here I written p as a function of z. I can p, I am interested on the value of p. So whatever p can be function of whatever it may be. So here I can also write p as a function of v dot dv. And I write here, I know the direction of pressure and direction of the force will also be same. So I write the vector PV as the magnitude of pressure dot direction of the pressure, that is minus K, dot the dV vector. Now dV, I have said earlier, dV vector is actually equal to A into dz, vector dz. Now vector dz is actually mod of dz into the direction of dz is actually upward direction, that is positive k direction. Now I have taken the reference that the bottom of the cylinder is z equal to 0. So when the gas is expanding, so dz is positive, so I can write mod of dz is equal to simply dz. Okay, so I can write vector dz is equal to dz into k vector, k unit vector k. So now I can write the incremental volume vector equal to A dz into k vector. So that is equal to dv into k vector. So now dw expansion will become pv minus k unit vector dot k vector into dv. So now the dot product will be minus k dot k, that is equal to minus 1. So it will be minus pv into dv. So this is for expansion. Now for compression, the derivation will not be much different. We say that since the work is always done on the system, so direction of the pressure will always be in minus k direction, that is downward. So dw compression will be equal to pv minus k vector dot dv vector. Now for compression, what will be the incremental volume vector? So we have defined, we can say Now in case of compression, the direction we can write dv vector as a into dz vector. Now in case of compression, the dz vector we can say this is actually mod dz into minus k vector, because the direction of dz is in downward direction. In case of expansion it was upward direction, that is why we wrote it as dz into k vector. Now it is dz into minus k vector. Now you see that mod of dz for compression is actually minus of dz compression, because z is decreasing, so mod of dz is equal to minus dz. So I can write vector dz equal to minus dz into minus k vector. So that is actually dz into k vector. So incremental volume vector now become a into dz into k vector. So our dw compression now become pv minus k vector into dv into k vector, that is equal to minus pv into dv. Now it becomes minus pv into dv. Now we see both for expansion and compression, the dw expansion is minus pv into dv, also dw compression is minus pv into dv. So now then how we see both have the same sign. Now our sign will depend on the initial and final volume. Now in case of expansion, dv is actually positive, so the total work will become minus a positive quantity, another positive quantity, so it will be a negative. So work of expansion will become a negative work. And in case of compression, we see dv is negative, and here the expression is minus pv dv, so minus into dv negative, so it will be total will be a positive work. So by which is actually we should have got, because work done on the system positive, so it means that actually in case of compression the external agency actually does some work. So that should mean work done on the system is actually means the compression work is positive, and work done on the system positive means the expansion work which should be negative, because in case of expansion the external agency actually does not work, the work is actually done by the system. That is why work done on the system will be negative for expansion.